Binomial distribution here today. The binomial is used to find probabilities of certain types of situations when these conditions down here are met, but it's used when we have multiple outcomes. You know, in chapter 4 we looked at our multiplication rules, but if we have 500 events occurring or 500 outcomes, we don't want to have to multiply a fraction by itself 500 times or find each of those individual ones. So the binomial is a formula that helps us simplify that process. First item here, a binomial, just as the name implies, bi can only have two possible outcomes, and those outcomes can be considered either a success or a failure. So for example, if I flip a coin, I have two possible outcomes, a heads or a tails. Now if I want to flip a coin and want to find the probability of it being heads, now heads is considered my success, that's the probability I'm trying to find, and tails will be considered my failure. So an experiment that has two outcomes that can be considered a success or a failure is a binomial. A couple other requirements here. There must be a fixed number of trials. So let's say I'm going to flip my coin 1,000 times. That's my n, or my total number of trials. The outcomes of each trial must be independent of each other. So each time I flip my coin, it still has a 50-50 chance of being heads. Doesn't matter whether I flip it the first time or the 500th time or the 1,000th time. Every time I flip that coin, it has the same probability of happening, that same 50%. And the probability of success must remain the same for each trial. Those 3 and 4 are essentially the same thing. They must be independent. They must be the same all the way through there. Not going to change from one event to the next. So here we have a formula, two different versions of it, n factorial over n minus x factorial times x factorial, and then times p to the x and q to the n minus x. The other version here, this part of our fraction, is the same thing as our combination formula that we learned back in chapter 4 as well. So NCX, or our combination's total number of trials, number we're trying to find the probability of happening, times our probability to raise the x power, and our q to the n minus x power. So a couple of items to note here. P and q are called complements. They add to be a total of 1. So p plus q equals 1. And then the x plus the n minus x, that should also add up to be our total number of trials. So our exponents should add up to be this number right here. We're just breaking our number of trials into these two different categories. So our number of trials is n. X is our number of successes desired, P is our probability of success, and Q is our probability of failure, or simply 1 minus P. Now along with our binomial, since we're working with a binomial, if we establish something as a binomial, we will also be able to calculate our mean, our variance, and our standard deviation. Variables real quick here, our mean is n times P, n is our number of trials, P is our probability of success. Variance is n times P times Q. Standard deviation is the square root of our variance, or the square root of n times P times Q. Here's what that looks like as far as our probability is concerned. For a certain company, workers miss 17% of the time. If one department has 12 employees, find the probability of no absences on a given day, and find the probability of 3 absences on a given day. Now notice here, our employees are either absent or they're not absent. So it is a binomial. We have two outcomes. Absent being our success, and not being absent being our failure, since we're trying to find the probability of absences on a given day. So down here, also notice we have two separate problems. Find the probability of no absences on a given day, and find the probability of 3 absences on a given day. So we're going to do those separately. Our first one, we'll find the probability of no absences. Our n, we have 12 total employees in the department. We're trying to find the probability of 0 absences. The probability of being absent is 0.17, which means the probability of not being absent is 1 minus 0.17, or 0.83. So our probability of 0 absences is 12C0 times our probability 0.17 to the 0 power to the x power, and 0.83 to the 12 minus 0, or to the 12th power. Now a little bit of a shortcut here. This one's kind of a simplified example, but as far as our calculator operations are concerned, 12C0 has a value of 1. Anything to the 0 power has a value of 1, so all we're doing is 0.83 to the 12th power, so the probability of 0 absences on a given day is about 0.107. We would then start over for problem number 2. Maybe I should label that as problem number 1 up there. Problem number 2 is the probability of 0 or of 3 absences on a given day. So I'd simply replace my x with the number 3, and the probability of 3 absences on a given day is 12c3 times 0.17 to the third and times 0.83 to the ninth. So notice my exponents of 3 and 9 add to be the 12, and there's my combination 12c3. If we plug this into our calculator using that combination function, we get a probability of about 0.202. So there's our first look at a problem with our binomial distribution. 2 possible outcomes, absent or not absent, and probably remains the same, 17% for each employee being absent. Let's move on here. There are 27 cars in America. 27% of the cars in America are some shade of blue. There are 10 cars in a parking lot. Find the probability that 5 of the cars will be blue. Okay, so the first thing, they're blue or they're not blue. 2 outcomes. Blue being our success, not blue being our failure. Our probability of being blue is 27%, so whether we're selecting the first car or the 10th car, our chance of being blue is still 27%. So down here, our N is the total number of cars in the parking lot, which is 10. Our X is the number we're trying to find the probability of being blue, which is 5. Our probability of being blue is 27, and our complement of that is 1 minus 27, or 0.73. So our probability of 5 being blue is 10c5 times 0.27 to the 5th, and 0.73, and 0.73 will also be raised to the 5th power because 5 plus 5 gives us 10. And if we plug that in, we get a probability of 5 cars being some shade of blue is about 0.075. Well, once we've identified the variables, plugging that into the formula is a fairly simple process. We'll move on here. 40% of a certain community is Hispanic. If 12 people are in a restaurant, find the probability that less than 4 are Hispanic. So being Hispanic is a success. Not being Hispanic is a failure. Binomial. 2 possible outcomes, Hispanic or not Hispanic. Regardless of who we select, there's still a 40% chance of being Hispanic, so that probability does not change from one trial to the next. Again, a binomial. So to write this down, N, there are 12 total people in the restaurant. We want to find the probability of less than 4. Well, numbers that are less than 4 are 0, 1, 0. I jumped ahead of myself there. 0, 1, 2, and 3. Those are all numbers that are less than 4. Our probability of being Hispanic is 0.4, and our probability of not being Hispanic then is 1 minus that, or 0.6. Now there is 12c0 times 0.4 to the 0 and 0.6 to the 12th plus 12c1 times 0.4 to the 1st and 0.6 to the 11th plus 12c3, oops, 2, I was going to 2 yet, times 0.4 to the 2nd and 0.6 to the 10th. And one more time, we have 12c3 times 0.4 to the 3rd, which means 0.6 is raised to the 9th. We're going to add those together. Now there is a table in the back of our book. That table starts on page 770. And that will also look up, that actually does these individual calculations for us once we've identified our variables. So let's take a quick look and see if I can find that table real quick. Right here. Let's rotate that. So we'd go, our N is 12, so we'd have to scroll down here. Rotate this one too. Still don't have our 12, so I should go one more page and rotate. And there is where 12 is at. I have to be able to see the top of this one. Our probability is up here at 0.4. So we go down to 12, and at 0.4, we find 0.002, 0.017, 0.64, 0.064, and 0.142. So those are our numbers, 0.002, 0.017, 0.064, and plus 0.142. Those, again, from the table, those are simply our calculations done for us right here. So kind of a shortcut. And if we add those two together, we get 0.225. So these numbers come either from the calculation or from the table, again, that starts on page 770. Now I'm going to pull that table back up one more time, possibly, noting this is a little bit different table. Ours in the back of the book does not have the 0.15, the 0.25, the 0.35. So there's only certain numbers that we can look up in here. If we go back to our previous problem, notice that 27% was not in that table, so we could not use the table for this problem. We can only use it for those numbers that are on there, on that table. On that, we'll have to use the formula. So one more time, 10% of the cameras sold in the United States are manufactured in Europe. If 20 cameras are selected at random, what is the probability that at least 3 were manufactured in Europe? N is 20. I'm going to come back to X. Our probability of being manufactured in Europe is 10, which means our complement is 0.9. Now at least 3 means 3, 4, 5, 6, 7, all the way up to 20. Now if we had to do that formula, that'd be 18 times. Not that it's impossible, writing that formula out and plugging in 18 times could be somewhat cumbersome. So we learned this back in chapter 4. We see this phrase at least 3. The opposite of at least 3 would be 0, 1, and 2. If we found those 3, we could simply subtract those 3 from 1, and that would make our job a lot easier. Doing the formula 3 times as opposed to 18 times would probably make a lot of sense. Even shorter yet, notice that 10% is in our table back here. So I'm going to have to scroll down yet another page or two and rotate those over. So let's rotate. Maybe. Having no luck here. Don't know why it won't let me rotate this. There we go. So let's rotate. And I don't know if I can see our probabilities. There are probabilities at the top. We have a probability of 0.1, which is this column right here. So we go down 0, 1, and 2, 0.122, 0.270, and 0.285. Now notice we scroll down in our book, these zeros are actually empty down here. Probability is so small, it's actually 0. So once we get down below 7, the probability is so insignificant at 0, it wouldn't be that bad to add 3 through 7 together, and that'd be our answer. But we'll go the route of 0, 1, and 2. So you find 0.122, 0.270, and 0.285. So we'll do 1 minus the 0.122, the 0.270, and the 0.285 from our table, and then that leaves us a probability of 0.323. So there's that at least, in this case, at least 3 idea. The opposite of being at least 3 is 0, 1, and 2. All right, moving on here. If a company has 200 employees and 17% are absent each day, find the mean and the standard deviation for the number of absences. So our mean, we plugged that out here just a little bit ago, was simply n times p, and our standard deviation was the square root of n times p times q. So identifying those variables, n is our 200 employees. Our probability of being absent is 0.17, which means our q is 0.83. Our mean then is 200 times 0.17, or we'd expect to have 34 employees gone on average every day. Our standard deviation is the square root of 200 times 0.17 times 0.83, and that gets us a standard deviation of about 5.31. So we're calculating mean and standard deviation of this distribution as opposed to finding the probability. One more time here, 56% of the people wear seat belts. If 50 people are randomly checked, find the mean and the standard deviation for how many will be wearing their seat belts. So again, our mean is n times p. Maybe I'll backtrack and identify those first. N is our 50 people. Our probability of wearing seat belts is 0.56, which means our probability of not wearing a seat belt is 0.44. Now we can find our mean, which is 50 times 0.56. or we'd expect to have 28 of those people not wearing a seatbelt. Our standard deviation is the square root of 50 times 0.56 times 0.44, and if we plug that in, we get a standard deviation of 3.51. So there's a quick look at our binomial distribution. Again, reminding us that binomials have two outcomes. Those outcomes are a success or failure. The probability of those outcomes is independent, and it remains the same for each trial, whether it's the first trial or the 10,000th trial. The probability stays the same all the way through.